This is the last part of the lecture covering non-constant acceleration. Let me just take you through two quick examples here regarding non-constant acceleration. Copy the first of those examples down into your notes while I read it to you here. Okay, the position of an object is given as the following function. Everything is in terms of meters. Let me write down the function. This function here, where everything is in terms of meters. It says simply find velocity and acceleration as functions of time. We have to take derivatives in order to do so. Before I do that, however, let's examine how the units are going to work in such a calculation. In this particular function, each of these terms here has to be in terms of meters. So let's take a look at the constants. The 3 by itself is in terms of meters. And now take a look at this quantity here, 14t squared. This is in terms of meters. So then therefore, if the t squared is in terms of seconds squared, what do the units of the 14 have to be? Well, the units of the 14 have to be meters per second squared. That is, meters per second squared multiplied by seconds squared then gives you something in terms of meters. Similarly, take a look at the -8 times t to the third. The t to the third is in terms of seconds cubed. So then therefore the units of the -8 have to be meters per second cubed, because then you'll have meters per second cubed multiplied by seconds cubed to then give you something in terms of meters as it should be. The reason why I'm indicating this is because, as we'll see, as these constants get dragged along in the calculations of the derivatives, the units get dragged along as well. And we'll see exactly how that works as we proceed. So now let's go ahead and find the first of our two functions. So velocity as a function of time is equal to derivative as a function of time, derivative of position with respect to time. So then therefore what I now have to do is use the rules for taking derivatives of polynomials, and we go term by term. Okay, first of all, the derivative of a constant is 0, and then we've got this term here. So then we take the 2 and we bring that down in front, like so, and then we take the value of the exponent and we lower it by 1, like so. Do the same thing with this term here. So first of all, I have -8, so let me write that. Okay, and then bring the 3 down in front like so, and then take the value of the exponent and lower it by 1. And now here's how the units of this quantity are going to work. We have right here 2 times 14 for a total of 28, but remember that the 14 is in terms of meters per second squared. So then we're taking meters per second squared and multiplying it by a time here in terms of seconds. That then gives us meters per second, as we should get for velocity. Similarly here, the -8 is in terms of meters per second cubed, and then we're multiplying it by seconds squared. That will then give us meters per second, as we should. So then therefore, if I clean this up a little bit, the velocity as a function of time is 28t, and then minus 24t squared meters per second, like so. Okay, and then lastly, we differentiate one more time to get acceleration as a function of time. So the acceleration as a function of time is the derivative of velocity with respect to time. So first of all, take the derivative of this quantity here. Keep in mind that this is t to the first, by the way. So when I take the derivative of this quantity here, I'm going to take the 1 from this exponent and then bring it down in front. And then take the value of the exponent and lower it by 1, so from 1 to 0. And then do the same thing here. So take the exponent and bring it down in front. Take the value of the exponent and then lower it by 1, like so. And then once again, here's how the units are going to work here for now, acceleration. Contained within all of this, keep in mind, was this 14, which was in terms of meters per second squared. And then we're taking meters per second squared and multiplying it by 1, so meters per second squared. Similarly here in this term, keep in mind that contained in here was our original -8, which was meters per second cubed, and then multiplied by seconds. That then gives us meters per second squared for acceleration, as we should. So in other words, all the units get dragged along in this process and end up then with the quantities that we should have. All right, so just cleaning this up here to finish the problem. The acceleration then as a function of time is just right here, a total of 28, and then minus 48 times t meters per second squared. So we end up with a non-constant acceleration here for this particular function. Okay, let's briefly take a look at the second function, or the second problem, that is, as well. Let me go ahead and show that here on my screen for myself. Okay, copy the problem down into your notes while I'm erasing here. In this case, we're given the acceleration as a function of time. Okay, so the acceleration as a function of time is given to us as 4 plus 3t meters per second squared. Okay, once again, let's check how the units are going to work here as we now integrate this quantity to first get velocity and then also arrive at position. It does say specifically, by the way, that the object starts at rest at the origin. So the original initial position, x0 is 0 for the origin, and it starts at rest, so the initial velocity is given to us as 0. These quantities are given, such that it makes the integration a little bit later on a little bit easier to do. Okay, now each of the terms here, in terms of the units, have to be in terms of meters per second squared. So the 4 by itself is meters per second squared. And then we have the 3. We're going to have here a total of meters per second squared, but the time is in terms of seconds. So then therefore I have to have the 3 in terms of meters per second cubed. So meters per second cubed multiplied by a time in seconds, then gives us meters per second squared, as we should. Okay, once again, we'll see these units get dragged along here in this process. Okay, we begin now in the following way. Acceleration is derivative of velocity with respect to time, and the first step in the integration process is actually algebraic. Move the time dt here to the left-hand side of the expression. Like so. Okay, and now we're going to go ahead and integrate. So on the left-hand side, we're integrating over time from 0 to t, and now on the right-hand side. On the right-hand side, the lower limit of integration for velocity is the velocity at time 0. That's specifically given to us as 0 in the problem. And then the upper limit of integration is the final velocity v. This is what we're going to find as a function of time. Now recall from the previous part of this lecture that the right-hand side of the expression here is always the same thing. That is, it's the change in velocity. It's the final value minus the initial value, which is 0 in this case. Like so. All of the work that you have to do in a problem such as this comes on the left-hand side of the expression, where I now have to take my acceleration and plug it here as the integrand of this function. Let me do this off to the side, like so. Okay, so here is my integrand now. Like so. Notice that I'm writing the constant 4 here as 4 times 1, which is the same thing as t to the 0th power, like so. So once again, we can use the simple rules for integrating polynomials. Okay, let's go ahead and find now the antiderivative of this quantity. So take the value of the exponent here and increase it by 1, and then divide by the new exponent. And then do the same thing with this term here. Increase the value of the exponent by 1 and then divide by the new exponent. We'll evaluate this then between 0 and t. Okay, let's go ahead now and plug the t into the function. And when you do, you just end up with the function itself. I'm going to clean it up a little bit here as we go. Like so. And then plug the 0 into the function here and subtract, and you just end up with minus 0. And now here's how the units are going to work. What we have here, first of all, is the 4 from earlier. That was meters per second squared, and we're multiplying it by a time in seconds. That then gives us meters per second, as we should. And then right over here in this term is the 3 from earlier. That was meters per second cubed, and then we're multiplying it by seconds squared. This then gives us meters per second, as we should when talking about velocity. So then this quantity here goes over here into the left-hand side. Like so. And then therefore the velocity as a function of time is just this guy right here. Like so. And it's all in terms of meters per second. Okay, now we do this process one more time to go from velocity to position. Okay, so velocity is the derivative of position with respect to time. begin by taking the dt here and moving it up to the left-hand side of the expression. Okay, and now we'll integrate. On the left-hand side, we're integrating over time from 0 to t. On the right-hand side, we're integrating over position. From, first of all, the initial position of 0, it says that the object starts at the origin, to its final position, x, like so. The right-hand side of the expression is always the same thing. That is, it's always the change in the position, in this case, x minus 0. Once again, all the work that you have to do here is on the left-hand side of the expression. We now have to take this quantity here that we found earlier as the velocity as a function of time. That then becomes our integrand here for this integral. Let me do this off to the side, like so. Okay, now we just use the rules here for integrating a polynomial to find the antiderivative. All right, so take the value of this first exponent and increase it by 1 and then divide, and then do the same thing here. And then we evaluate this between 0 and t, like so. Okay, once again, begin by just taking the t and then plugging it into the function, and when you do, you just get the function. And then subtract with the 0 plugged in here, and you just simply end up with minus 0. Okay, let me clean this up a little bit. And you end up with this quantity here. And then here's how the units work. Okay, keep in mind the 4 from earlier, which was in terms of meters per second squared. So meters per second squared times seconds squared gives you then position in meters. Okay, and then over here in this term is the 3 from earlier. Remember that was meters per second cubed. So meters per second cubed times seconds cubed then gives you a position in meters as we should. So once again, all the units here work out. This guy here then goes over here into the left-hand side of the expression. Like so. And then just writing this out formally, the position as a function of time, then therefore is just this. All in terms of meters. And now we have all 3 functions, position, velocity, and acceleration in each of these 2 examples. Then we can calculate whatever it is that we're looking for in some kinematics situation. Okay, this concludes the series of lectures on non-constant acceleration. This completes for us Chapter 2.